Hi, in the last video, I discussed about how do we do simple linear regression. What does that mean? That means if there is one dependent variable and one independent variable, so dependent variable we denote by x, sorry, y, right? And independent variable we denote by x, okay? So if there is one dependent variable y and only one independent variable x, that is called the simple linear regression. And then we tested the hypothesis if the y, the dependent variable, depends linearly on x, meaning that whenever the value of x increase, then the value of y increase or decrease with certain slope. Okay, so that's what we did. Also, we talk about the confidence interval of the regression coefficient, which is beta, right? And also the prediction interval for the predicted value, or the line of best fit, right, that we call the regression line. We also found the prediction interval of that regression line as well. So the next thing is, sometimes the dependent variable may depend on more than one independent variable. Okay, for example, the area of a rectangle depends on both length and width, right? If you increase the width, length, area will increase. If you increase the length, then area will increase. So in that case, the area depends on two variables, length and width. Okay, so, and there are so many other examples that a dependent variable may depend on more than one independent variable. And then the dependence may be linear or non-linear. In this course, we will talk about the linear regression only. So what I'm going to do next is I'm going to talk about the multiple linear regression. That means that y depends on more than one x variables, but linearly. Okay, you see that in multiple linear regression, one of the variable depends upon two or more than two variables. Okay, if the dependent variable y depends on independent variable, if there are like x1, x2, x3, x4, and xm, so on, then the multiple linear regression equation for the population has the form. For the population, the multiple linear regression, previously we had just y equals to alpha plus beta x, right? Now we have more xi's, so beta i's as well. So yj will be alpha plus beta 1 x1j plus beta 2 x2j, and so on. And the corresponding equation for sample will be yj, actually we denote by y hat here, right? Y hat j equals to a plus b1 x1j plus b2 x2j, and so on. In the R software, we use the same method we did in this simple linear regression, except dependent variable is written as x1 plus x2 and so on. And also if we have to do the interaction, then we'll have to do x1 and then colon x2. Okay, you have the concept of the interaction from the ANOVA. And the test, to test the hypothesis, the null hypothesis is again beta I equals to 0. What does that mean? That means the relation between y and x1 will be beta 1, that is the regression coefficient. Y and x2 will be beta 2, and so on. Okay, and then beta I not equals to 0 is the alternative hypothesis. So working multiple regression needs a lot of computation, so we directly use R only. I'm not going to show you how to do manually. Okay, so what are the assumptions of the multiple linear regression? So there must be linear relationship between the outcome variable and the independent variables. This should be related linearly. Okay, scatter plots can show whether there is a linear or curvilinear relationship. Multivariate normality is multiple regression assume that the residuals are normally distributed. Next is no multicollinearity. Multiple regression assume that the independent variables are not highly correlated with each other. This assumption can be tested using variance inflation factor VIF values or by running correlation between two variables. So you can check the test the correlation between any two variables, or you can find out the variation inflation factor. Okay, and another is homocydasticity. This assumption states that variance of error terms are similar across the values of the independent variable. A plot of standardized residual versus predicted values can show whether points are equally distributed across all values of the independent variable or not. So we'll discuss that in the lab. Okay, So the next thing we will be discussing here is the how do we do, because do you remember that whenever we do the ANOVA or t-test, there was there was a parametric test, right? Also, some of the parametric tests could be used to do the categorical variable, right? And in the ANOVA, there was Kruskal-Wallis test that could be used for the non-quantitative, non-metric data, right? Also, in the correlation, we had rank correlation coefficient, right? If the data is ordinal data is also factor data or categorical data. In that case, you know how to find out the correlation coefficient too. Okay, so in the regression analysis also, we can analyze the categorical data, even if it is nominal data or ordinal data. We can do it. Usually we do for the quantitative data or the metric data, but if the data is nominal or ordinal, then we can still do the linear regression analysis. Okay, you see that usually many of the independent variables in the regression problems are metric or at least ordinal, but if the independent variable is nominal, then we need to code the variable as a dummy variable with n-1 separate columns, where n is the number of levels. This is when you do by hand, but when you use R, it is just similar to the previous simple linear regression or multiple linear regression for the numerical variable. Okay, dummy variable assign numerical value to levels of categorical variable. If case falls in a level, we write 1, otherwise 0. Manually, we consider each level as a variable. What it means is, let me show you a simple example. Suppose you have, let's say, gender, sex, and then let's say blood pressure. Okay, suppose there are 20 people, let's say. So first subject is male, his blood pressure systolic is 120, let's say. The second is also male, his systolic is 132, let's say. The third one is female, and then the systolic blood pressure is 116, and so on. Okay, so in this case, we don't have, so this is like X, this is like Y, right? This is like Y, but there is no number here in the X. So what you do instead of that is, let me write down Y variable first, that is 120, 132, 116, and so on. That is the blood pressure. So we are trying to check if the blood pressure depends on the gender or the sex or not. Okay, so this is Y variable. So X variable, what I want to do is I want to create a dummy variable. Dummy variable means we assign a number for these values. Let's say male is 1, female is 0. So what we write is 1, 1, and then 0, and so on. For male, you write 1, 1, and for female, you write 0. Usually, how many levels are here? Here are 2 levels. Male and female are the 2 levels, right? If there are 2 levels, we call binary. Okay. In case of the binary, we need only 1 column for the dummy variables. If it has 3 levels here, for example, race, in that case, you can have 2 of these, like write x1 and then x2 and so on. Okay, and then do that if there are 3 levels in the gender, and then you find out the correlation. We do the regression analysis on this data set after you change into the numerical. Okay, that's what it is saying. All right, so we can also plot the scatter plot for each of the level of the categorical variable and compare the impact of level to the output variable. Okay, not part, output variable. Okay, guys, so that's the end, but I will spend a little more time on the R code. Okay, let us talk about this difference between regression and correlation. So regression, the meaning is, correlation is statistical measure which determines the correlationship or association of the 2 variables. Regression describes how an independent variable is numerically related to the dependent variable. So usage is to represent linear relationship between 2 variables, and regression is used to fit a baseline and estimate one variable of the basis of the another variable. Dependent and independent variable, no difference in the correlation, because if you find out the correlation coefficient between X and Y or Y and X, you get the same value. And here in the regression, you get different values. So one should be dependent, other should be independent. You should figure that out before you do the analysis. Okay, indices, correlation coefficient indices indicates the indicates correlation coefficient indicates the extent to which the 2 variables move together. Regression indicates impact of a unit change in X on the variable Y. Okay, and objective is to find out numerical value that express the relationship between the variables. and the other one is to estimate values of random variable on the basis of values of fixed variable. Okay, that is the end. So the next thing what I'm going to do here is I am going to show you how to do the regression analysis, multiple regression analysis using R directly. Okay, let us do that. All right, so for the multiple linear regression you need at least three variables. One is dependent variable that depends on the other variable, and then there must be more than one independent variable, more than one x values. Okay, and then we work on that. Okay, so let us talk about one example. This example I'm taking stack loss, and then what is the meaning of what type of data is this? That's the stack loss data. It says Brownlee stack loss plant data. So the data is from operational data of a plant for the oxidation and ammonia to nitric acid. Okay, oxidation of ammonia to nitric acid. So so here there will be three variables, four variables actually, four columns. One is the airflow, next is the water temperature, another is the acid concentration. Okay, so this is in the degree centigrade, I think. This is the flow of the air. I'm not sure how, they didn't mention how, what is the unit of this. Okay, and acid concentration is per 1000 and minus 500. Okay, whatever they measure, but we are just trying to find out the, in whatever unit, trying to find out if the stack loss is the output variable, that is the y variable, if it depends on airflow, water temperature and acid concentration or not. That's what we want to do. So all these variables are numerical variable. Okay, let us look at that. A is that, and then if you do the stack loss, okay, and you see that there are four columns, all of these are numerical columns, all these are numbers here. You see that? Now our goal here is we want to test if the stack loss data depends on airflow, water temperature or acid concentration or not. That's what you want to test. Okay, this is just an example of multiple linear regression. So what do you do? It is just straightforward. The y variable should be written first, and there is a wiggle sign, same as the simple linear regression. Okay, and then write down the x1. What is x1? X1 is the airflow plus water temperature plus acid concentration, and then what is the data? The name of the data is stack loss. Data equals to stack loss. So this is what you do. Only the difference is you do plus whatever variable you want to test for the dependency. Okay, and then you can just add those plus and the name of that. Okay, again all these variables are numerical variable, and I will give you examples of if one of them are categorical variable and one of them are numerical and so on. Okay, all right, let me run this. You see that I ran it, but I didn't see any output result, right? So we need to do summary and then the name of that model. I named as linear model 1. Okay, if you do that, then what do you get? You got, let me make it a little up. So what do you think here is, it says that, so without, okay, without any of the airflow, so let me write down first this way. Okay, so what I want to see here is what are the p-values for airflow, water temperature and acid concentration. Okay, so for airflow the p-value is less than alpha, for water temperature the p-value is less than alpha, for acid concentration p-value is greater than alpha, meaning that acid concentration does not have a significant linear impact to the stack loss. That's what we say. Okay, and also what we can say here is for every unit increase in the airflow, then you will have 0.7156 increase in the stack loss. Okay, similarly for water temperature, for every unit increase in the water temperature, you will get 1.2953 unit increase in the stack loss. That's what it says, because it is a linear regression. Those are like a slope. These are like a slope for each of these variables. Okay, for this one I'm not saying anything because it is not significant. Okay, we actually immediately remove the non-significant variable, and then we do, look at this, as the p-value of acid concentration is greater than 0.05, it is not significant not statistically significant dependence. Okay, let us remove it and run the regression for only two of those, only this one and that one. Okay, let us see that. I ran with the airflow and water temperature only, and I did that. What do I get? I got that this is significant, this is also significant, both are less than alpha, right? So what you can say from here is airflow and water temperature. Let me say this way: the stack loss, that is the y variable, stack loss dependent linearly with airflow and water temperature, and the dependence is statistically significant, okay, with these p values, right? What you can say here is for every unit increase in the water temperature, 1 degree centigrade unit increase in the water temperature, you get the stack loss increase by 1.2954. Similarly, every 1 unit increase in the airflow, the stack loss will be increased by 0.6712. Okay, so if there is no airflow and no water temperature, then the stack loss will be decreased by 50.3588. Okay, that's what you get. Why? Because look at this, stack loss is y, right? Stack loss is y. That's what we did that. This is y variable. These are the x1, x2, like that. Okay, you see that stack loss equals to alpha a plus bx plus bx1 plus cy1, right? You see that? Look at here. So this is a, right? If there was only one variable, then it will be y equals to a plus bx. But there are two. That's why you have y equals to a plus bx plus bx1 plus b1x1. Let's say b1x1 plus b2x2. That's what you get, right? And what you get here is basically, you see that if there is no airflow and no water temperature, okay, if it is 0, then what you get is, what is left is all these things will be 0, right? You will get the stack loss will be decreased by negative 50 point, decreased by 50.36, like that. Okay, if there is just airflow but not the water temperature, then you will remove this part, okay, and you keep just this equation y equals to a plus bx, and then you can find out, you can answer any question there. Similarly, if there is no airflow, just the water temperature, then you can just remove this part and keep the first term and that term only. Okay, so let us describe what we got here. Stack loss depends linearly on airflow and water temperature with average 0.671 increase per unit increase in airflow and 1.2954 increase per unit increase in the water temperature. Without airflow and water temperature, the average decrease in stack loss is 50.3588. That's what you get. Okay, guys. All right. So that's what we got. And then if you want to find out the 95% confidence interval for this is linear model 1, right? Let me do linear model 1 there. So if you do the if you want to find out the prediction interval for the y values, this is what you do. You linear model 1, and the stack loss is the name of the data, and the interval is the prediction interval, right? So this is what you get for each of those y values. These are the lower bound and water bound. And if you want to find out the confidence interval for beta values, what is our beta value? So beta 1 is 0.6712 and beta 2 is 1.2954. If you do the confidence interval for the linear model 1, this is linear model 1, we named it 1, right? Oh, by the way, no, let's see. Let's do for linear model 2, because I want to do both, because I said that at the linear model 1 we had 3 independent variables, and we found that the acid concentration is not significant, right? That's why we removed that and we just took 2 and then we named it linear model 2. So I'm finding the prediction interval and then confidence interval for the linear model 2. That is with the only 2 variables, okay, 2 independent variables. You see that? So for airflow, these are the 95% confidence interval, and for water temperature, these are the 95% confidence interval. Okay, these confidence interval does not contain 0. That means that it doesn't contain the null hypothesis, right? That means that it is significant, statistically significant. Okay, guys. All right, that's what we got. Now we want to do the test of assumptions. Okay, guys. So what were the test of assumption? Let me review that first. So what were the assumptions? Assumptions were So normality of the residuals, right, and no multicollinearity of the independent variables. Also the linearity of the independent variable and dependent variable, right, and also the equality of the variances, right. So those were the assumptions that we discussed. Okay, all right. So let us look at the multicollinearity of the independent variables. Multicollinearity can be assessed by computing a score called the variation inflation factor, all called VIF. Okay, for each of the variable you find out the VIF. So again, I'm not going into the detail of that. So I'm just using that. Okay, which measures how much the variance of a regression coefficient is inflated due to multicollinearity in the model. So the smallest possible value of VIF is 1, okay, 1, which is if you get VIF close to 1, then there is no multicollinearity. And as a rule of thumb, a VIF value that exceeds 5 or 10 indicates a problematic amount of collinearity, okay. That's how we measure the no multicollinearity. Okay, for this you need to install a package car first if you don't have already. And if you have installed a package car already, then you can write library car and then do VIF and then the model, linear model too. Okay, let us do that. What do you get? So we got 2.57, 2.57 for both airflow and water temperature. Okay, so we are good. So variance inflation factor is close to 1. So we are good here. Okay, now what we want to do is we want to check the normality, linearity of the variables, normality and so on. So if you do linear model 2 and then comma 1, that will show the plot for the residuals versus the fitted. Okay, if you see the increasing pattern or the decreasing pattern here for the red line, then you see that there is a problem. But if it is not, right, I mean it is not a perfect data set, but it is close to the dotted line, right. And for the second one is the QQ plot. It will look like it is along the normal line, right, so it is okay. And the last one is the homocydasticity. You see that again, so it is not increasing or decreasing everywhere. It is showing it is not showing a pattern, right. You see that the data are almost equally scattered everywhere almost. Okay, so I'm assuming that this problem, the data set does not violate the assumptions. Okay, so the next thing is sometimes we look at if there is the interaction effect, or we also call the modification effect. Okay, so I am taking the same data set, I'm doing airflow plus water temperature plus airflow and then that column sign water temperature. That means you're trying to see the interaction effect. Okay, if you run this, what do you get? So you get that interaction effect, that is the p-value for the interaction effect is greater than 0.05, right? You see that? So it is greater than 0.05, meaning that there is no interaction effect. It looks like we do not need interaction term because it is not significant, that is p is greater than alpha. So the model without interaction should be considered. That's what we should consider, that work we should be considered no interaction effect. Okay guys, all right. So the next thing that I want to do is, so we just saw an example if all the independent variables in the multiple regression analysis are numerical, all of them are numbers. Okay, but if the numbers, if some of the data are numbers, some of the independent variables are numbers, some of the independent variables are categorical. Under categorical there may be nominal or ordinal data. Okay, in that case we still use the similar technique. Okay, very much similar technique, but before you do the linear regression, you can plot and find out get some of the idea from the plot as well. Okay guys, all right, let us see that of the independent variable as a